There we go. You can put them on that middle table there, Mason.
Which one?
That middle. Yeah. All right, take a look up here. Everybody look up here. One thing as a person, whoops. So you're taking chemistry, and some of you, many of you will take it in college. It's hard to say how much time the professor would spend on individual experiments. Some professors would. They would get into this. They'd want you to say, you should know these experiments well, or something like that. Some of these are really classic. Some people that changed how chemistry was taught, one of them was Avogadro, and the other one was Gay-Lussac. And these two people together, they came up with this idea about gases. For example, see that blue box up there? I don't know if you remember that, but that's not molar mass, but it's molar volume. And so what they figured out was that if you had the same volume, if you had the same volume of any gas, any kind of gas, carbon dioxide gas, ethane gas, helium gas, whatever the gas was, it didn't matter. If it was all the same temperature and pressure, then equal volumes would have equal number of particles in it. So they did a lot of experiments where they took one volume of gas and combined it with one, or one volume of gas with two. And then they saw how much product they got. And that changed chemistry because it entered into the world of the mole. The world of the mole was discovered by these experiments right here. Does that make sense to you that if I had a box like that, and it had helium in it, and it had a box like that, it had carbon dioxide in it, and a box like that, and it had, methane in it, all right? The three completely different gases, but if they're at the same temperature and pressure, they'd have the same number of particles. And how many particles would that be, though? And standard temperature and pressure is what they call 1 atmosphere of pressure and 0 degrees Celsius. So if you had standard temperature and pressure, and you had that box that big, and you had all three of those gases, how many particles would be in each box? I'm looking at your eyes a little bit. I'm looking at your face, and what are you thinking here? What do you think, Parker?
What's the question?
So see that box there? Let's say I had three different kinds of gases, or helium, methane, carbon dioxide. And they were at standard temperature and pressure, which is 0 degrees Celsius and 1 atmosphere of pressure. How many particles would be in that box if I put helium in it?
22.4.
Okay, now 22.4 would be the volume, liters. That would be the volume in liters, wouldn't it? But how many particles would be in there? Okay, that's fine. That's fine. What do you think? Rollins, what do you think?
6.02 times 10 to the 23rd.
Exactly. And you would have a mole. You would have a mole of particles. Now, again, once they figured that out, all of a sudden the idea of the mole came into play. And I was trying to tell you this before, very few chemistry students, for whatever reason, I didn't, but when I look at that number for aluminum, 26.98, that means two things. It means one atom of aluminum has a mass of 26.98 what?
Grams.
Don't ever say that. 1 atom will never be 1 gram, okay? 1 atom is tiny. A paper clip is a gram, isn't it?
Yeah.
All right, let me go here. McKinney, what do you think? 1 atom of aluminum weighs how much? And we actually had this last chapter. Look up here. Look up here. How many?
1 AMU.
Wait, just a minute. Now, McKinley, 1 atom of aluminum weighs how much? And if you look up here, and the reason I told you that is that a lot of students, for some reason, they missed this. And it says here 26.98 AMUs.
On average.
Yeah, okay, all right, because they're isotopes. Because they're isotopes, right? And so that's how much it weighs in AMUs. But the connection that they made, and this is what neat. If I gave you not a million, not a trillion, not a billion, but if I gave you 6.02 times 10 to the 23rd of those, it would weigh a whole lot of AMUs, wouldn't it? So many AMUs that it would equal.
It can go into grams finally.
Yes, it'd be 20. It'd be 26.98 grams. So if I had a mole of aluminum, it'd be that. So what I'm trying to tell you here that when you read this, when they ushered in the idea of the mole, it took that little world, whatever's going on in the little world, in the world of mass, we can expand it now into the world of grams, and we can do experiments in the world of grams, and it tells me what's going on in the little world. And so that really changed chemistry. Okay, anyway, as far as history, I don't want to do too much every day, but this guy here, J.J. Thomson, anybody remember what he got credit for? Yes.
Wait, why did they pick 6.02 times 10 to the 23rd to be the number?
They didn't pick it. It's just that's what they discovered. I see. That's a great question. That's a great question. That's a great question. Why did they, at that temperature, why even, what a weird number to pick, 22.4. Who wants to pick that? But it happened to be the mole. That's a great question about, even Avogadro, sounds strange, even Avogadro, his number was discovered later by someone else, but we call it Avogadro's number. No, Avogadro, I say. Now you're thinking of the person who invented guacamole. You're thinking, yeah, right, is that right? All right, get that one. That's right.
So what was, I'm sorry, what was the answer?
No, that's
Basically, I
right.
don't know.
6.022.
Basically, it's just a number.
Okay, here we go. You know what? I don't have an answer. That's a good question.
Could I research it?
Why did they wanted it? I know they wanted it to be, but they could have picked something else. They could have picked something else, and then those numbers would be something else, wouldn't it? I think once they locked in on the mass of an AMU, then that's what happened. So when they, that's another story. They could have picked hydrogen, protium. They could have picked hydrogen and said, "That's my standard. I'm 1, and if you're 5 times bigger than me, you're 5, and if you're 11 times heavier than me, you're 11." They could have done that. I think they thought, though, why don't we take another atom that's a little bigger, that was stable, and they put carbon 12. So carbon 12 became the standard of all things. So carbon 12 had 6 protons and 6 neutrons. And they said, that's going to be 12.000, that's my standard, okay? Now, if you're twice as heavy as that, then you're going to be 24. So once they established what an AMU was, then that's where all these numbers came from. But then, to get into the gram world, how many of these AMUs did you need? And that's a great question. How many AMUs do I need to equal a gram? And if you think about it, 1 atom of hydrogen has a mass of about 1.07 AMUs. Multiply that times 6.02 times 10 to the 23rd, and you'll get how many AMUs it takes to make a gram, wouldn't it? So, even though that's a great question you had, Mason, because I don't know the exact order, but once they established the mass in the tiny world, then that was kind of locking everything in. Yeah, that's a great question you had. I don't know if I answered it very well. Yes?
There goes Russia.
Okay, anyway, real quickly, this guy here, J.J. Thomson, if you'll take a look at this picture, and I'm going to, there you go. By the way, this yellow, these 2 pages of yellow, it's kind of neat because this guy named Berzelius, he had to do with, before Berzelius, people had their own little symbols for sodium and stuff like that, and he kind of established a system in which you would have that, like we see today, a single letter, and so he kind of established a symbols for the elements and compounds like that. Let's take a look at J.J. Thomson's thing. I think it's still amazing to me that someone thought, boy, you know what? Somehow I think if I could get somebody to build this glass container, and back then that was not that easy. And then, by the way, I'm going to tell them to seal in a wire and a piece of metal in it. Yeah, somebody's got to learn how to do that. And then it's got to be made so well that you can take all the air out of it and seal it so it's a vacuum. It's like, what? You're going to do all this trouble? Why? What makes you think something's going to happen? But something in his thinking says, I think if I hook this up to electricity, something's going to happen. Now, where'd that come from? But what did happen? What did happen when he hooked this up to electricity and excited all these atoms? All these atoms in the metal were excited. And then a beam appeared. A beam appeared in that tube. This is called a cathode ray tube, which is essentially a vacuum tube. And what was that beam made of? You might say, well, I don't know. I'm not sure what the beam was made of, but look over here. Look at this picture here. And I have all this stuff on my desk. So then he did something kind of interesting. He has this beam, and then he says, I'm going to hook up a magnetic field. It could be electromagnetic field. An electromagnetic field, you know why it's better than just regular old magnets? For an electromagnetic field, you can actually increase or decrease the electricity, increase or decrease the magnetic field, and you can do some calculations. You see that? If I just have a plain old magnet, like a bar magnet or something, I can't tell what's going on. I can't change it either. And so they use electromagnets. So here you have a magnet, and this beam's coming through here, and it seems to be attracted to the positive pole and be repelled from the negative pole. So what did J.J. Thomson, what did they eventually call that particle? They said something from these atoms is being released from the atom. The atom is neutral, but whatever is being released is not neutral, because look what happens. In a magnetic field, it tends to be attracted to the plus and repelled by the minus. So this thing in here must have what charge?
Negative.
Right, and these are incredibly smart. Something is coming from the atom and has a negative charge, and it's forming a beam. And that's how he got the discovery of the electron. Have I got that? So anyway, cathode ray tubes, until about 20 years ago, everybody had something like that in their house. TVs were big, and they were cathode ray tubes. And computer monitors were big, weren't they? They were like big, and they were cathode ray tubes. And essentially what that means is you have a vacuum tube, and you shoot electrons toward the screen. And that's what a cathode ray tube. So it's called a CRT. But now they got rid of, almost nobody uses CRTs anymore. Okay, you had your hand up, I'm sorry. Did you have a question?
Oh, what's the name of that, shit was called a cathode ray tube? Is that what it's called?
What's the name? J.J. Thomson?
No, the name of the device.
It's a cathode ray tube. So a cathode ray eventually became the word electrons. Okay, I'm gonna. I think I'm gonna stop here with the scientists, but it's actually interesting. I used to think that the history of science was so boring, and I just didn't want to hear about it. I didn't want to hear about all this other good stuff. But the more I'm in science, I really enjoy the human endeavor. That how in the world do you discover things like this? And I think that's what excites people more about science than just some of the facts. So the history is actually interesting. Yes?
So what's in a TV now if it's not the electrons?
Okay, so they have two kinds. They have plasma TVs, and then they have, what's that other word? LED. They have LED TVs and plasma TVs. Now,
There's a lot more than just LED.
it's not, we don't have a vacuum anymore where you're shooting electrons. And I know you don't believe this because I had trouble believing when I first knew about it. When I was growing up, they had black and white TVs. And that was a single beam being shot at the screen, and it would say glow, glow, don't glow, stay dark, or it'd be black, white, and gray, black, white, gray, and it would go like this. The cathode ray with a magnet, an electromagnet would say, and it would write the picture many times a second. If you had a really high-speed camera, you could actually see a bar. My brain couldn't see it, but a high-speed camera, you could see where you interrupted the picture being written. It was written over and over and over, over and over and over, over and over and over. And you said, "Wow, it can't be right," but it was.
That's how, are like.
You'll see you would see a bar where the one picture, they just got done writing that picture and they're starting another one.
Yeah, that's what.
And then somebody came up with the idea, could we put 3 electron guns in there? And then in the front of the screen, we would have a red, blue, and green, they had a name for them. Darn it, not pixel. They had red, green, blue, I can't remember the name. Anyway, so now you got 3 electron guns, and they're all writing a picture. And if you had red only, it looked red. But what if you had red and blue? And it was like purple. And they could make every color you want for a color TV, and the same thing would happen. They rewrite the picture over and over and over and over. Today's technology is different. LEDs are different, but there's no electron gun. There are electrons, electricity flowing through it. But, and I don't want to get into this. There's also LCD. Have you heard of liquid crystals? Okay, so liquid crystals, when you put a certain amount of electricity, they'll go like this. They'll rotate. And they'll block the light or let light through. And you can actually rotate liquid crystal TVs. Anyway, so TVs now are flat because they're not using the gun. They're not using the CRT. All right, let me stop with history for a minute. You should spend a little bit of time with these because, like I said, every year people they underestimated knowing the people in the history part. All right, I'm going to finish this, and I'm going to call you up to take the thing. We're going to play the grid game here a little bit. Before we do that, let's finish the world of charge. This is where we were yesterday. Take a look up here. We had finished the world of mass, and we went into the world of charge. And so we go over here, and so we have this thing called a metal, and we know that over 75% of the elements in the periodic table are metals. So metals have a tendency to lose electrons. They have some, especially their outer electrons are loosely held. That makes them good conductors of electricity. It also makes them good conductors of heat. And anyway, so in a chemical reaction, they tend to lose electrons. Now, it doesn't mean a piece of copper is going to lose electrons sitting here. But if you put it in a situation where something's willing to rip it away from you, then you'll tend to lose electrons. And usually it's 1, 2, or 3. So take a look at lithium. Before we started, lithium has 3 protons and 3 electrons, so it's neutral. It's a neutral atom. But what would happen if I put lithium in contact with something like chlorine? Now, chlorine has 17 protons, 17 electrons. It has no charge. But what happens? Nonmetals have a tendency to rip other people's electrons off. They want to gain electrons. And so what happens here is lithium is very famous for losing 1 electron. It's hard to get rid of more than 1 for lithium. Now, if it loses 1 of its electrons, it has 3 protons and only 2 electrons now, giving it an overall +1 charge. So the lithium atom has now become a lithium ion, hasn't it? Lithium ion. And now this ion is called a cation, and this whole thing has a positive charge. Now over here, I now have an extra electron. I have extra negative things, so I become an anion, and I have this. So one of the more, I would say the more frequent chemicals that form in inorganic chemistry are these salts. And salts are ionic compounds. What do you think ionic compounds are made of? Starts with I.
Ions.
That's right. So when you have a metal ion, a cation, and a non-metal anion, the nature of what holds them together. Hey, I kind of wanted to lose that electron anyway, and I kind of wanted to gain. Why don't they just say, see you later, get away from me? They can't get away from each other. Why not? What is the nature of the ionic bond?
Negative.
And?
Positive.
That's right. So this electrostatic attraction is actually a very strong bond. What I think is interesting is if you try to break that bond with heat, ionic compounds, usually you have to heat them up a lot, like 500 degrees to break that bond. And yet, what happens when I put a grain of salt in water?
It dissolves.
It becomes
I know, but what's that
sulfur.
mean?
It's a compound.
the ionic compound, if it's soluble in water, an ionic compound, the ions will come apart and be surrounded by water and become salt water, won't it? And it'll have sodium ions in it and chloride ions in it. Yes,
So is this a redox reaction?
I can't hear it, wait.
Is this a redox reaction?
Okay, that's a great question. Even though we will review redox. Redox means, remember redox? You know what redox stands for? Oxidation reduction. And what's Leo says GER? What's Leo stand for? If you lose electrons, so who got oxidized? Lithium got oxidized, and then gain of electrons, who got reduced? Excellent, good memory. And this is a redox. Okay, this is a redox reaction, which we have that in another chapter. We'll definitely do it. Great job. Now, the nature then of an ionic bond is the attraction of these ions. So I have some salt. I have some salt here. This is the most famous salt. But every ionic compound between a metal and a non-metal is an ionic. In the end of this chapter, you'll find out there are some polyatomic ions that also act like ions. And so what would sodium nitrate be? NaNO3. Sodium plus ion, nitrate minus ion. It's still a salt, isn't it?
Yeah.
And it's just the most common salt, NaCl. But any ionic compound is a salt. And if it's soluble in water, water's ability to tear you apart, to break that bond, is greater than the ability of the ions to keep themselves together. And yet, weren't there some chemicals on that chart? Remember that chart right there? Weren't there some chemicals that when you put them in water, they're insoluble? They're salts. But guess what? The ability of water to take them apart is not greater than the ability of the ions to hold themselves together. So they are insoluble. I need your attention because that's some of the most common things I see in second year chemistry. They casually think they understand that. And when I tell them, what is NaNO3 aqueous? What's NaNO3 aqueous? What's in that beaker?
Sodium.
Okay, what's floating around that thing is sodium ions that are surrounded by water and nitrate ions that are surrounded by water. And there is no sodium nitrate in that beaker. There's sodium ions and nitrite ions. Okay, so what we're going to do, I decided not to give you a quiz today. Thought about it. I don't want to quiz you as long as we're staying together, but I do want to make sure I want you to bear down a little bit more in this chapter. So what we'll do is we'll come up here, and I'll do the first one, and then one at a time, just come up, and you can pick any one you want, and we're going to finish out now we're doing this. All right. In the grid game, we look for information. And what we have here, and in the 10th grade, I'd probably have you do a little check mark here. You guys are big boys and girls now. You don't have to put a little check here. But on the other hand, why don't we start out doing the check marks so we don't forget something? Okay, the first thing, here's my clue. I would not look at any numbers at all. I would look for the symbol if it was there, okay? So if I have a symbol, okay, so I look for, if I have a symbol, capital C, here's something I'm always sure about. This is called the alwayses. Capital C will always have the atomic number of 6. I cannot fool you with that. And the atomic number is always the number of protons. I cannot fool you with that. So here are 3 things that are always connected. The symbol, atomic number, and protons is locked in. You can't be fooled. So my opinion is, if you do the alwayses first, there we go, I did the alwayses. Now you can attack either the world of charge or the world of mass, whichever one you want to go after next. In the world of mass, and that's up here, right? I know this thing has a mass number of what?
12.
There's 12 things in the nucleus, and I know 6 of them are protons, so what?
6 neutrons.
And that's a coincidence, right? It didn't have to be 6, does it? And now I'm done with the world of mass. Now I go to the world of charge. Uh-oh, I don't see anything. Well, wait a minute. If you have 6 protons and you don't see anything, what does that mean?
6
electrons.
You have to have 6 electrons. See? That was pretty easy, wasn't it? All right. let's start with McKinley. You come up, you pick anyone you want, and then you're on deck, Rollins, okay? And so let's kind of see if we can do these. Remember the game in 10th grade? I'm doing it again. You're not allowed to write anything on the paper unless you tell everybody how you know what that is, okay? All right, so let's start it.
Okay. Wait.
Everybody listen. Listen.
Go McKinley.
Thanks for volunteering to be first, McKinley.
You're so welcome. Okay.
Also, when you're doing these, you might want to write in one color pen what was given, and another color pen what you had to come and figure out. All right, McKinley, I'm ready.
Okay, the symbol is C, so the atomic number has to be 6.
It always?
Always.
Okay.
And that means there has to be 6 protons.
Wait, always?
Always.
Always check the always things.
Most
You
of
don't
the
have
Check
always
off
things.
the always.
You don't have to.
Yeah, it's sort of.
All right, now what world do you want to get into now?
Let's go to the world of mass.
Okay.
So the mass number is 14.
Always?
Not always.
Right.
Oh.
That is right.
We already did the always.
So,
Which
this isotope has a mass of 14.
which means there has to be 8 neutrons
Why?
because the protons and neutrons are the mass number.
All right.
And since there's no charge, there has to be 6 electrons.
Oh man, this is great. This is great. All right, go. Here we go. Let's keep it going. We're trying to get all these done.
This isn't a
Trying to
trivia,
get them all
you're
done.
I don't know.
And you know what? You can do, Rollins, you can do any one you want. You don't have to do the next one. You
Can you
can
throw
do
me
any
a
one you want.
pen?
I would love.
Thank you.
All right,
Okay,
everybody listen? Wow.
so
Everybody listen?
the atomic number. What? I'm gonna do this one.
Okay, go.
Okay, the atomic number has to be 11
Why?
because that's what it is on the periodic table.
There's a lot of things on the periodic table.
Well, that is what it is.
Huh? It's 11 for what?
The amount of protons
For who?
for sodium.
Oh, why? Oh.
Okay, the protons is also 11. Check off the always.
So they're always the same?
Yes, and then
Wait, the electron, the proton, the atomic number is always the same as protons?
Mhm.
Okay, all right. There we go.
Yep. The number of the mass number is 22.
Wow.
So the protons plus the neutrons has to equal 22, so that'd be 11 neutrons.
Okay.
And then
Check off
the
the
number, oh, there we go.
You don't have, I don't mind starting out that way, we don't have to.
Okay, now since it has a plus 1 in the top right,
Listen.
that means there's one more proton than there is electrons.
Oh, nice.
So that means there are 10
Man, you guys
electrons.
look good here. All right, go.
Go, Marie, go, go,
All right,
go.
Run!
Go.
Run!
Hurry,
Run!
hurry.
Run!
Tell
Run!
One, matter of fact, why don't we
Check the
have,
table.
hey, wait, why don't we have the on-deck person, get a stool over here.
Oh,
You're
good
next.
idea.
You be ready, right?
Great idea.
What is innovation? Be ready after. Now, Marie, you can pick any one you want.
Okay, I'll do the oxygen.
Okay, all right.
Okay, so the atomic number is 8
For what?
for oxygen.
Always?
Yes, always. And so that means there are 8 protons, always. And then the mass number is 16.
Always?
No, but that's what we're given.
This
so.
one, this one.
Yeah. So that means there are going to be 8 neutrons, and then the charge is -2, so that means there are 2 more electrons, so that's 10
Excellent,
electrons.
excellent. All right, go, next. Mason,
Mason, you're on deck.
I'm going, jeez.
you pick any one you want.
I think I'll take the uranium. That is a U, right?
Nope.
So that is a 92, as you can see up there. So your atomic number is going to be 92, and your number of protons is 92, because they always equal, always, always, always.
For what?
Say what?
For what? It's always 92 for what?
Uranium.
Oh, okay.
Yeah. Your mass number is 235, because it says it over there. And then your number of neutrons is this number minus that number, which is 232, 142? 143. And then you have a +2 charge, which means you have 2 more neutrons, which means 90 electrons.
Two more neutrons? Wait, 2 more what?
You got 2 more protons.
Okay. All right, good job.
Neutrons. Mason,
Hi, Jeff.
you didn't check off all the boxes.
Oh, is there not already a pencil up here?
His job is to tell you to check off the box, but he didn't.
Yeah. Come on.
It's for the more basic.
All right, let's go.
Is there a
We're just
a pen
Come on.
or a?
All right,
Never mind, I got it.
All right,
So-
come on.
We were really worried.
So this is
Wait a minute, you're not.
Whoa.
Joe!
okay. So okay. So I'm gonna explain.
Why?
So it's the atomic number is 9 because you look up there.
Parker, get out of the way.
Pretty sure he's wrong.
Parker, you're on deck. Move over.
Wait, I wanna listen, I need to listen to what he says.
So you see up there,
I'm a little confused.
it's absolute. So no matter
Well,
what.
You know why fluorine has the atomic number 9?
Enlighten us, Jim.
9.
I've
Wrong.
You know why?
because it has 9 protons.
What kind of atom universe has 9 protons?
Well, since the atomic number is 9, that means it has that amount of
That's right.
protons. It's always
Spitting
like that.
facts.
You gonna take off that olive
Yeah.
box?
So
What about the 18? Is that always 18?
no, you look over. It says 18.
Alright, so this isotope is 18.
Yes.
What is that?
So if you see the charge is -1, so that means
Are there more pluses or more minuses?
there is one more minus.
Okay.
So that means there is 10 electrons, and then there's 9 neutrons because 9
That's a
plus
good
9
nine.
equals 18.
No, wait a minute. Even though,
Fix that 9.
hey, everybody listen.
It's a pretty good 9.
Wait.
9.
Stop. Even though I'm not gonna tell anybody what order they should do it in, okay? But I do notice that you didn't finish the world of mass, and you went into the world of charge, and then came back with neutrons. And I'd be a little careful of that on a test. If you're a little bit nervous, I would try to make sure I finish the world of mass and then charge. Because if you let them mix them together, you're gonna have problems.
Yeah.
You did a good job. All right, let's go on.
Yeah.
All right.
So you
next
gotta
one.
get on deck.
Now, the next one,
Yeah, that's facts
even
for real.
though I told you that you're supposed to look at the symbol first without the numbers, here we don't have a symbol. So I wanna hear what you have to say about this one.
So the mass number
Stop.
always equals
You're gonna have trouble finishing that sentence.
so
Great start, Parker. Great start.
that means the mass number for whatever element is
Very
2.
Very good.
So I'll put a 2 right there for
Come
now.
on, gotta hurry.
And then
Hurry.
neutrons, that means the neutrons and the protons are the same. So that's 1. And that means that one's 1. And so that means 1, if I go to my trusty periodic table,
Okay,
1 is hydrogen.
okay.
So hydrogen is 1. And then there's 0 electrons. So I think that's it.
You forgot a little something.
There's a charge.
There is a charge,
Really?
which is
Why?
because there's 0 electrons.
Oh, so that would be.
So that means there would be,
Hey, click.
Hey,
Parker,
everybody stop.
there's one
Stop.
proton.
Wait.
yeah, so there's +1, right? Yeah.
Why is it +1?
Because there's one more proton than electron.
Okay, all right, here we go.
Alright, get out of the way.
All right, Clay, going up there.
So the mass number is 1, so we know it's right here. Since the mass is 1, we know that there has to be 1 proton since there's no
Okay.
neutrons,
That's true.
which we know that's hydrogen. And then we know that because there's no electrons, it is +1. And then we can check off all our boxes along with Parker's and everyone else's.
All right, good, very good, all right. You're gonna do one that says a single proton. All right, go.
Me?
Yeah, a single proton, that's all you get. No, don't write that in there.
Oh.
Good job, Clay. Great start.
Oh, I see it now.
Perfect before that.
I see it now. I am sorry.
Can you do me a favor and see the camera?
Oh yeah.
No, it's okay. I looked at it tilted.
All right, go.
Oh, that you gave me a difficult one. Okay.
Proton.
Well,
It's
a single
difficult to
proton
break
is gonna be
You
hyd.
did it again.
This pencil doesn't work.
It does.
Can I? Who's red?
Mine.
That was his.
Clay, come on.
But yeah, I
Okay.
fixed
A single proton
Stop, please.
is gonna be hydrogen. The mass number is gonna be 1 because there's only
Wait,
one.
what made you say hydrogen there?
Because common sense. Oh, because hydrogen has 1 proton.
Well, let's put 1 down there for protons then.
Yeah.
And the atomic number is always the same for protons and atomic
Okay,
number.
okay.
So I was
Alright,
working
keep
a few
going.
steps ahead. Okay. The atomic mass is going to be 1 because there's no neutrons, because it's just a single proton, which means there are 0 neutrons. And number of electrons is also 0 because there is no electrons. And the mass number is 1. And oh wait, where was charge? Oh, charge is -1. Or sorry, +1 because it's a proton.
Okay, all right.
Ten.
Thank you. All right, thank you. All right, thank you. That's very good.
Ten.
Thank you. All right.